Gas companies, electric utilities, and oil suppliers control how you survive every winter. But in Finland, engineers just proved that ordinary sand heated to 600 degrees can warm 100 homes, and the physics says you can replicate it for $300. 900 kilograms of silica sand, one temperature swing, 37 kilowatt hours of stored heat. It all comes down to a single number most people have never heard of. Silica sand, the same mineral used in glass making and playgrounds, holds a secret that matters far more than most realize. Its ability to store heat is determined by two numbers. The first is specific heat, 830 joules per kilogram per degree Celsius. This means every kilogram of sand absorbs 830 joules of energy for each degree its temperature rises. The second is bulk density, 1,750 kilograms per cubic meter. In practical terms, a single shovel of sand packs a surprising amount of mass, and with it, the potential to hold a large amount of heat. These numbers are not just theoretical. They come straight from industry material data sheets and have been measured in laboratories around the world. Specific heat sets the upper limit for how much energy you can store in a given mass of sand. Density determines how much sand you can fit into a tank, a barrel, or a backyard pit. When multiplied together, these values reveal why sand is so effective. It stores more heat per cubic meter than most common materials, and it does so without boiling, corroding, or breaking down at temperatures that would destroy water tanks or plastics. This combination of high specific heat and solid density means that even a modest pile of sand, say 900 kilograms, can absorb enough energy to keep a small, well-insulated home warm for days. The physics is simple, but the implications are profound. Each degree of temperature rise in a sand mass translates directly into stored heat, and every cubic meter becomes a silent reservoir, ready to release that warmth slowly over time. The entire system is anchored in these two constants, and they are the foundation for every calculation that follows. A single worked example lays bare the numbers that drive the sand battery's promise. Imagine 900 kilograms of dry silica sand sealed inside a steel tank. If that sand is heated from a chilly 20 degrees Celsius up to 200 degrees Celsius, the math is simple but powerful. Mass times specific heat capacity times temperature rise. That is 900 times 830 times 180. The result is 134 million joules, about 37 kilowatt hours of stored energy. To put that in context, 37 kilowatt hours is enough energy to run a 1,500 watt space heater non-stop for a full day, or to cover the daily heating needs of a small, well-insulated home in the heart of winter. This is not hypothetical. The calculation uses industry-verified constants, and it is the same formula that engineers apply when sizing commercial systems. The only variables are how much sand you use and how hot you are willing to run it. The temperature rise is critical. Every degree above room temperature adds more stored energy, but also demands better insulation and a drum that can handle the heat. At 200 degrees Celsius, the sand stays safely below the limits of ordinary carbon steel. And the system remains simple: no pressure, no risk of boiling, no exotic materials. The entire heat reservoir sits quietly in a drum that costs less than a single month's utility bill in many cold climate states. This is not just theoretical storage. The 134 megajoule figure is a real-world benchmark. It is enough to keep the radiators warm, the pipes unfrozen, and the living room comfortable through multi-day storms. With each recharge, the cycle repeats, giving the homeowner a predictable, measurable buffer against the cold. Deep in the Finnish town of Kankaanpää, a steel silo filled with 100 tons of dry silica sand stands as proof that the sand battery concept is more than just theory. The Polar Night Energy pilot heats its sand core to between 500 and 600 degrees Celsius, monitored by dozens of thermocouples embedded at every level. During the brutal Arctic winter, this single installation delivers heat to around 100 homes, pushing warmth through the district's radiators while outdoor temperatures plunge far below freezing. The system's round-trip efficiency, measured by independent audits and verified by the Finnish Energy Authority, clocks in at roughly 85%. That means nearly all the energy put into the sand during charging is recovered as usable heat over the season. The battery's discharge curve shows a slow, controlled release. Temperatures fall from 600 down to 250 degrees over 5 months, with a final drawdown to 150 degrees during peak demand. Throughout the winter, the battery delivers a steady 2 to 3 kilowatts of heat per home, enough to keep living spaces at a comfortable 20 degrees Celsius. Mikko Lane, a dairy farmer who relies on a smaller version of this technology, describes the relief of seeing his entire barn and home heated for 130 days straight, without touching the grid or burning a drop of oil. The numbers are clear. 100 tons of sand, charged once, keeps a whole town warm through the darkest months. Field data from Finland doesn't just validate the physics, it demonstrates that, with the right design, sand batteries can survive and perform in the harshest real-world conditions. A $310 sand battery isn't a fantasy, it's a shopping list. The core of the system is a standard 55-gallon steel drum, widely available for around $80 new, or less if you find a used one. Into this drum goes 900 kilograms of kiln-dried silica sand, purchased in bulk for about $66. The heat moves in and out through 30 feet of Schedule 40 steel pipe, a $135 investment that handles high temperatures without deformation or corrosion. Surrounding the drum, a 4-inch thick ceramic fiber blanket, rated to withstand over 1,000 degrees Celsius, costs about $70 when sourced from a specialty supplier or bought as a single roll. A basic temperature controller and a high-temperature thermocouple add $30 to the bill, allowing you to monitor and regulate the system without guesswork. Add in high-temperature silicone for sealing, a handful of clamps and bolts, and a slab of concrete to support the weight, and the total lands between $250 and $310, depending on local prices and whether you buy new or salvage parts. No exotic materials, no specialty tools, just a grinder, a pipe cutter, and a weekend's worth of determination. The entire build, from pouring the foundation to sealing the last clamp, takes about 14 hours. Every component is off the shelf, every step is documented, and the total cost is less than a single winter's heating bill in many regions. The barrier to entry isn't money or expertise, it's the decision to get started. A sand battery's week-long autonomy relies on 3 charging paths: solar thermal, wood-fired heat, and photovoltaic electricity. Each brings its own rhythm to the cycle of storage and demand. A 2-kilowatt evacuated tube solar collector, positioned to catch the winter sun, heats sand to nearly 300 degrees Celsius. With about 50% efficiency, it delivers 1 kilowatt of heat, enough to recharge a 900-kilogram drum in 38 hours of strong sunlight, covering 2.5 days of heating with 3 days of clear skies. Where sunlight falters, a rocket mass wood heater steps in. Burning wood at high efficiency, it pushes 3 to 5 kilowatts at 350 degrees Celsius into the sand through a steel manifold. A single 3-hour burn can add 12 kilowatt hours, meeting a full day's need. 2 firings a week, alongside solar input, keep reserves steady through cold spells. Photovoltaic panels offer a third route. A 2-kilowatt array, wired to a resistive coil, turns surplus electricity into heat, though only 18% of sunlight becomes stored energy, requiring 4 to 5 days of sun for a full charge. Hybrid use ensures the battery meets daily winter demand. Burying a sand battery transforms the ground into a natural insulator. The steel drum, filled with 900 kilograms of dry silica sand, is set into a shallow pit and wrapped in a ceramic fiber blanket rated for over 1,000 degrees Celsius. This keeps the U value below 0.05 watts per square meter per Kelvin, the same standard required for commercial thermal storage. Compacted soil slows temperature swings, while the entire 1.5-ton assembly rests on a concrete slab that distributes weight evenly. A 30 psi pressure test confirms airtight welds and seams, meeting industry benchmarks for safety and durability. Upkeep is minimal. Once a year, an air compressor pressurizes the system to 30 psi. If the gauge holds steady for half an hour, the drum and manifold are sealed tight. Ceramic insulation rarely needs replacement before a decade or more. Corrosion rates, measured in both lab and field, average less than 0.02 millimeters per year. A 2-millimeter steel wall loses only a fraction of its thickness in 20 years. A Minnesota Building Code official classified the buried battery as a non-pressurized, fire-rated vessel. Surface temperatures remain far below the 260 degrees Celsius safety threshold, and the earth barrier prevents accidental contact. Maintenance takes minutes, not hours, and the system quietly delivers a 20-year service life. Right now, millions face rising winter bills and grid failures, while a $300 drum of sand can quietly store enough heat to last weeks, without fossil fuels or monthly costs. As energy insecurity grows, the question isn't if this works, it's who will build it first. What's stopping you?